Welcome to Module 5, the exciting world of generative AI. This is arguably the most talked about and rapidly advancing area in AI today, transforming how we create, innovate, and interact with information. So, what differentiates generative AI from the AI we've discussed so far? Up till now, most AI has been discriminative AI. Discriminative models learn to distinguish between different categories or predict a numerical value. Think of them as classifiers or predictors. They take an input and predict an output based on patterns and existing data. For example, a discriminative model might classify an image as cat or dog, or predict a house price. It's about drawing boundaries or making predictions from existing data. It answers the question, what is this, or what will happen? Generative AI, on the other hand, is about creation. These models learn the underlying patterns and distributions of a dataset so well that they can generate new, original data that resembles the training data but is not identical to it. They answer the question, what can be created? This means generative AI can produce realistic images of faces that don't exist, write coherent articles, compose music, design molecular structures, or even create entire virtual worlds. It's about moving from analysis to synthesis, from prediction to creation. The ability to generate novel content unlocks immense creative and practical possibilities. It's empowering artists, designers, writers, scientists, and businesses in unprecedented ways. We'll start by exploring some foundational generative models before diving into the power of large language models. Let's begin. Before the explosion of large language models, two foundational architectures laid much of the groundwork for generative AI: Generative Adversarial Networks, GANs, and Variational Autoencoders, VAEs. Understanding them provides crucial context. Let's start with Generative Adversarial Networks, GANs, introduced by Ian Goodfellow in 2014. The core idea is brilliant. It's a two-player game, an adversarial process between two neural networks, a generator and a discriminator. Imagine the generator as a counterfeiter trying to produce fake money that looks real. The discriminator is a detective trying to spot the fake money. The generator takes random noise as input and tries to produce realistic-looking data, for example, an image. The discriminator receives both real data, for example, real images, and data from the generator, and its job is to correctly identify whether an input is real or fake. These two networks train simultaneously, in competition. The generator learns to produce increasingly realistic fakes to fool the discriminator. The discriminator learns to become better at distinguishing real from fake. This adversarial process continues until the generator becomes so good that the discriminator can no longer reliably tell the difference. At this point, the generator can produce highly convincing, novel data. GANs are renowned for generating incredibly realistic images, from human faces to landscapes, and can even translate images from one domain to another, for example, converting a horse to a zebra. However, they can be challenging to train due to their adversarial nature. Now let's look at Variational Autoencoders, VAEs. Unlike GANs, VAEs are probabilistic models that learn a compressed, continuous representation of the input data, called a latent space. They consist of an encoder and a decoder. The encoder maps input data, for example, an image, into a distribution in the latent space, typically a mean and variance for each dimension. The decoder then samples from this distribution and reconstructs the original input. The VAE is trained to ensure that the latent space is well-structured and continuous. This well-structured latent space is crucial for generation. By sampling new points from this latent space and passing them through the decoder, VAEs can generate new data that resembles the training data. VAEs are known for their ability to generate diverse outputs and perform smooth interpolations between different generated samples.
while GANs excel at photorealism and VAEs at diversity and smooth interpolation. Both were instrumental in advancing generative modeling. They demonstrated the feasibility and power of teaching machines to create, paving the way for the sophisticated large language models and diffusion models we see today. Next, we'll dive deeper into LLMs and their transformer backbone.
If you've been impressed by AI generating human-like text, answering complex questions, or writing code, you've witnessed the power of large language models, LLMs. These are at the forefront of generative AI for text, and they are built almost exclusively on the transformer architecture. Recall our previous discussion on transformers. Their ability to process all words in parallel using self-attention and their scalability made them ideal for training on vast datasets. LLMs take this to an extreme. They are transformer models trained on colossal amounts of text data, billions of words from the internet, books, articles, code, and more. The large and LLM refers to two things: the scale of the data they're trained on and the number of parameters they possess. Models like GPT-3 have billions, even trillions of parameters, allowing them to capture incredibly subtle patterns and relationships in language. What do LLMs actually do? At their core, they are highly sophisticated next word prediction machines. Given a sequence of words, an LLM predicts the most probable next word. By repeatedly predicting the next word, they can generate entire sentences, paragraphs, or even full articles that are coherent, contextually relevant, and grammatically correct. Their strength comes from their deep understanding of language structure, grammar, facts, common sense, and even subtle nuances learned from this massive training data. This emergent capability allows them to perform a wide range of tasks: text generation, writing essays, stories, marketing copy; summarization, condensing long documents; translation, as we've seen, but now with even higher fidelity; question answering, providing informative answers to queries; code generation, writing code snippets or entire functions. Let's revisit the transformer architecture for LLMs. Many LLMs are decoder-only transformers, meaning they are primarily focused on generating sequences. They have a stack of decoder layers. Each decoder layer uses masked self-attention, ensuring that when predicting the next word, it only attends to preceding words in the sequence, not future ones. Self-attention is critical. For any word in the input-output sequence, self-attention calculates a weight or score for every other word, indicating its importance relative to the current word. This allows the model to dynamically focus on relevant context words. This is done through query, key, and value vectors derived from each word embedding. Multiple self-attention heads are used in parallel, multi-head attention, allowing the model to focus on different types of relationships simultaneously. Perhaps one head focuses on grammatical dependencies, while another focuses on semantic meaning. The outputs of these heads are then concatenated and linearly transformed. After self-attention, the output passes through a feed-forward neural network for further processing. Each layer also incorporates residual connections, allowing information to skip layers, and layer normalization, which are crucial for training very deep networks. The result of this complex, multi-layered transformer architecture, scaled up with immense data and compute, is a model capable of generating astonishingly human-like and contextually relevant text. The final output layer typically uses a softmax function to predict the probability distribution over the vocabulary for the next word. LLMs are the driving force behind the current generative AI revolution, impacting everything from personal assistants to creative writing tools. Next, we'll learn how to effectively communicate with these powerful models through prompt engineering. Large language models are incredibly powerful, but they're only as effective as the instructions you give them. This brings us to prompt engineering, the art and science of crafting effective inputs to guide generative AI models to produce desired outputs. Think of a prompt as a conversation starter, a set of instructions, or an example that tells the AI what to do. A well-engineered prompt can unlock the full potential of an LLM, while a poorly designed one can lead to irrelevant, inaccurate, or uncreative responses.
Here are some key principles for effective prompt engineering. Be clear and specific. Avoid vague language. Instead of write something about dogs, try write a 10-word persuasive essay about why dogs are the best pets for families, focusing on loyalty and companionship. Provide context. Give the AI all the necessary background information. Who is the audience? What is the tone? What is the purpose of the output? Specify format. Tell the AI exactly how you want the output structured. Generate a list, write a paragraph, format as JSON, use bullet points. Define constraints. Set boundaries. Keep it under 200 words. Use simple language. Exclude sensitive topics. Don't use any cliches. Provide examples, also known as few-shot learning, is one of the most powerful techniques. If you show the model a few input-output examples, it can learn the pattern you're looking for. For instance, translate this, hello, into hola. Translate this, goodbye, into adios. Translate this, thank you, into chain of thought prompting. For complex tasks, break down the problem into smaller, logical steps. Tell the AI to think step by step or provide intermediate reasoning examples. This helps the model to perform multi-step reasoning. Iterate and refine. Prompt engineering is an iterative process. If the first output isn't right, don't give up. Refine your prompt by adding more details, clarifying instructions, or trying different phrasings. You can also ask the AI to revise its own output based on your feedback. Mastering prompt engineering turns you into a conductor for these powerful AI orchestras. It allows you to steer their immense capabilities towards your specific creative and analytical goals. Now, let's explore how generative AI goes beyond text to create stunning images and multimedia. Generative AI isn't limited to text. It's revolutionizing the creation of images, video, and other multimedia content. This is a rapidly evolving area, democratizing digital art and design. While GANs were pioneers in image generation, a newer family of models, diffusion models, has taken the lead in producing incredibly high-quality and diverse images. Models like DALL-E, Midjourney, and Stable Diffusion are all based on this concept. How do diffusion models work? Imagine taking a clean image and gradually adding random noise to it until it's just pure static. The diffusion model is trained to reverse this process. Given a noisy image, it learns to iteratively remove the noise step by step until a clear, high-quality image emerges. This denoising process is guided by text prompts. So you provide a text prompt like a futuristic city at sunset, cyberpunk style. And the model starts with random noise, then guided by its understanding of the prompt and its learned ability to denoise, it gradually transforms the noise into an image that matches your description, adding details and refining features over many steps. These models are incredibly versatile. They can generate images from scratch, in-paint, fill in missing parts of an image, out-paint, extend an image beyond its original borders, image-to-image translation, transform an image based on a prompt, like turn a sketch into a photorealistic drawing. Beyond static images, generative AI is also making strides in video generation. While more computationally intensive, models are now capable of generating short video clips from text prompts, or even animating still images. This has huge implications for content creation, filmmaking, and animation. Furthermore, generative AI is being used for audio generation, music, voice cloning, and sound effects, and even 3D model generation, creating virtual objects and environments from simple text descriptions. This pushes the boundaries of what's possible in virtual reality, gaming, and industrial design. The creative possibilities unlocked by these multimedia generative models are staggering, empowering artists, designers, and marketers to produce high-quality content rapidly and efficiently. It's truly a new era for digital creativity. Now, let's explore broader applications of generative AI.
Generative AI is not just a technological marvel, its applications are incredibly diverse and impactful, transforming industries from creative arts to scientific research. Let's explore some key areas where Gen AI is making a difference. In content creation, generative AI is a game changer. From generating marketing copy, social media posts, and product descriptions to drafting articles, scripts, and even full-length novels, LLMs are significantly accelerating content production and offering personalized variations at scale. For art and design, image generation models empower artists and designers to rapidly prototype ideas, create unique illustrations, generate concept art, or even produce entire digital artworks from textual descriptions. This democratizes high-quality visual content. In software development, Gen AI is assisting developers by generating code snippets, translating code between languages, debugging, and even writing entire functions based on natural language descriptions. This boosts productivity and helps automate repetitive coding tasks. Synthetic data generation is a powerful application. When real-world data is scarce, sensitive, or difficult to obtain, Gen AI can create artificial data sets that mimic the statistical properties of real data. This is invaluable for training other AI models, especially in healthcare or finance, where privacy is paramount. For personalized marketing and customer experience, Gen AI can create highly tailored content, ad copy, and product recommendations for individual customers, leading to more engaging and effective campaigns. Chatbots powered by LLMs provide more natural and sophisticated customer support. In scientific research and drug discovery, generative models can propose novel molecular structures for new drugs, design new materials, or simulate complex biological processes, significantly accelerating the research and development cycle. From aiding medical diagnoses by generating realistic patient scans to assisting architectural design with automated layouts, generative AI is pushing the boundaries of what's possible, fundamentally changing creative and analytical workflows. Now, let's examine specific generative AI case studies. To bring the power of generative AI to life, let's look at 5 groundbreaking real-world case studies where it's already making a significant impact. Case Study 1, ChatGPT by OpenAI, the most widely recognized GenAI application. It uses a large language model, GPT series, to engage in conversational dialogue, answer questions, write essays, summarize text, brainstorm ideas, and even write code, demonstrating remarkable versatility across numerous text-based tasks. Case Study 2, Mid-Journey for visual content creation. Mid-Journey is a popular AI art generator that takes text prompts and transforms them into stunning, high-resolution images. It's used by artists, marketers, and individuals to quickly generate unique visual assets for various purposes, from concept art to marketing campaigns. Case Study 3, GitHub Copilot for Code Generation. Developed by GitHub and OpenAI, Copilot is an AI pair programmer that suggests code snippets, completes lines, and even generates entire functions in various programming languages based on comments and existing code. It significantly boosts developer productivity. Case Study 4, AI in drug discovery. Example, in silico medicine. Companies like In Silico Medicine use generative AI to design novel molecules with desired properties, accelerating the identification of potential drug candidates. This dramatically reduces the time and cost associated with early-stage drug discovery, leading to new treatments faster. Case Study 5, Synthesia for AI video generation. Synthesia allows users to create professional-quality AI videos from text. You type a script, choose an AI avatar, and the platform generates a video with a speaking presenter, complete with lip syncing and natural gestures. This is transforming corporate training,
marketing videos, and news delivery. These examples showcase the incredible breadth and potential of generative AI, from augmenting human creativity to accelerating scientific breakthroughs. We've now covered the core of AI and ML. Our final module will touch upon reinforcement learning and the critical topic of AI ethics.